So we were looking at last time, the short five lemma, which, let me recall for you, what it says is, if this is a commutative diagram and both rows are exact, then if the two ends, if the two bookends are onto, the middle one's onto, and if the two bookends are 1 to 1, then the middle one's 1 to 1. We proved onto last time, and this is a diagram chase, so we're going to do a couple of these today. I love doing this actually. We proved that if these two are onto, then this one is onto last time. So let's suppose these are 1 to 1. We want to show that this is 1 to 1. So suppose let A2 be in a kernel of G2. So here's what I got going for me. That goes to 0. Now, my goal, of course, ultimately is to prove that A2 itself is 0, right? So what do? Well, this goes to 0 here, and there's not much else I can do except push this down the road, which I will do. This goes to some A3. And how about A3? When I push it down, where does it have to go? 0. It has to go to 0. And here we're using the fact that the diagram means, because going this way certainly gives 0. So going this way has to give 0. So what can we conclude about A3? And the kernel of G3 is 0 because G3 is assembly 1 to 1, right? So what does that allow us to leverage here? So now we know that this guy is 0.
You should use exactness at A2.
Right, that's right. That means that A2 is in the kernel of F2. This is the image of F1. So I don't know much, but I know that there's some A1 over here that goes to A2. Well, of course, I want to show that A2 is 0. I don't have that going for me yet. But let's chase this around the other block. All right. Where does this go? I don't know. So I'll call it B1. But I do know what? B1 must go to 0, right? Because this goes to 0, so this path leads to 0 as well. But H1 is 1 to 1. So the kernel of this is 0. So that means that B1 is also 0. Well, what does that mean about A1? A1 is 0 because this map is 1 to 1. And so A2 is the image of 0, which is 0, and so is 1. Okay, so that takes care of the short 5. Basically what you have to do in your homework, one of the things you have to do in your homework is the 5 lemma. But there's exactly enough information in these last assumptions. In the 5 lemma, these are perhaps non-zero modules, but there's some assumptions on the vertical maps being either 1 to 1 or onto, and it's just enough for you to be able to get this out. Okay. This next result, and I think it would probably be obvious why we call this, is called 3 by 3. Theorem 6. Let's suppose that we have a commutative diagram of R module homomorphisms. Now, following commutative diagram. R module. A1, A2, A3, B1, B2, B3, C1. Further, C3. So we got this 3x3 thing. So we have the following, A, if the columns and bottom two rows are exact, so the top row. So if all the columns are exact and, the bottom two rows are exact and the top row is exact, and there's kind of a mirror image of that in the following sense. If the columns and top two rows are exact, so is the bottom row. Okay. So let's prove, I'm gonna prove half of this, and the other half's in the homework. And actually, I think that me showing you this here will probably give you a pretty good clue about how to do the other one. It's kind of dual. So, but I do want to point something out in this. We go along. So, going through. So this is gonna be work for you guys doing the homework, right? Because you probably have to tell me what the maps are, and I'm gonna be a little, like, name the maps, and I'm gonna be a little fast and loose with this. So I'm going to assume, I'm gonna do part A, so I've got the columns and the bottom two are exact, and we'll do the top. Now let me think about this here. Okay, so I'll just go through this. One of these, so what do we have to do actually? So let me kind of organize this to show that the top row is exact. I'm just gonna call this F and G. We need to show that F is 1 to 1. 2, we need to show G is on to. And sort of exactness in the middle, we have to show image of F is contained in kernel G, and 3B, kernel G is contained in the image of F. And those last two steps get you exactness in the middle, right? And so I want to, by the way, this one's almost always one of the easier things to do. And this one's always almost always more difficult. Yes. So, let's see. Okay, yeah, I think I'm gonna approve G is on today. So let's let A3 in. Now, what do I know? Well, I need to get something back here that goes to it. And really, lucky me, there's only one way to go with this, right? So I can just push this down here, B3. Right. What's my next move, perhaps?
Pull back.
That's right, because I know that the bottom two rows are exact, right? So I don't know much, but I know that there's B2 that goes here, right? Now, gosh, it would be really groovy if I could find something here that goes to B2. And I can, right? But it's not readily obvious. Any ideas on that we might have to do here?
So C2, C3.
Okay, so I can certainly push it down here, agree? And what happens when I push V3 down here? What do I get? I have to get 0. Why do I have to get 0 here?
Exactly, so the column.
Right, this column is exact, so V3 is in the image, so it has to be killed in this next step. So that means the C2 pushes to 0. Right? Okay,
We have this C1 goes to C2.
what's that? Ah, right. So that means the C2 is in the kernel of this last map. So I did pick the hard one first. So there's a C1 here that goes here. Okay. Okay,
Then we get a B1 because that.
it's a B1. Okay, so now what? Well, now we almost seem stuck, but you know, really, the good thing about this is I'm looking at this unholy mess that I've got so far. And really, the only thing I can do is push this B1 on here. Now, there's no particular reason when it goes to B2, but it goes to some B2 prime, right? Right, it goes to something here, but it may not equal this B2, right? But what do I know?
B2 minus B2 dash goes to 0.
Right, you're actually, forgive my pea-sized little brain, you're ahead of me one step here. This has to go, to C2 as well, right? And so by his observation, B2 and, B2 prime go to the same place, right? So let me write this down. Notice that, these go, if I push vertically, this goes to 0. So there exists, let's say, A2 such that A2 goes B2 minus B2. So, different color here. B2 minus B2. Okay, so how does that help? Okay, so let's take B2 minus B2 prime and push it this way. Where does that go? If I look at B2 minus, if I push this way, where does it have to go? Why does it have to be B3?
Because B2 prime should be in the kernel.
That is right. B2 prime, so when I push it this way, B2 prime's dead, right? And B2 I already know goes to B3. So this goes to B3. Everybody okay with that? Because this homomorphism takes B two to B three, and it takes B two prime to zero, so it goes to B three. And that's gonna do this, right? Because now A two goes to X, because I'm tired of subscripting stuff. And so it has to go to B three as well. So. Right, so,
Not this one to one.
right. So A three, goes to B three. And X goes to B three. And so A three equals X. These two things go to B three, this map is 1 to 1, so these two are the same. So in particular. I was trying to show that this thing is onto, and I freaking visited every module on my diagram, except for A1, right? Do I agree with that? Crazy. That was such a mess that I'm like, probably worth it for me to just do it over. But is everybody okay? Is everybody okay on the ontos? Okay. Now, I want to make an observation here. So next step, what I want to do is I want to show, F is 1 to 1. Okay, so let's let A1 and of course, ultimately, I want to show that A1 is, yes.
I was thinking that another way to do it without, so first, we're gonna think that
Are we talking about this one now?
Yeah.
Okay.
the map that goes to, from A1 to B1 is 1 to 1, right?
Mm-hmm,
And the one that goes from B1 to B2 is 1 to 1.
mm-hmm.
So the composition of that two is 1 to 1, 2. But that's equal to the map that goes from A1 to A2 and well,
That's exactly right. This one, watch this, right? So F of A1 is equal to 0. So this pops over here to 0, correct? Well, let's see what happens here. This goes to B1, and B1 goes to B2, right? If we just chase it this way. Right? But by the commutativity of the diagram, B1, that is B2 must be 0. Agree? But this map is 1 to 1. And so B1 is 0. And this map is 1 to 1, so A1 is 0. And we're done. Right? So all this used is commutativity of the diagram to get 0 here, and the fact that these two on the corners are 1 to 1. Notice the 1 to 1 part of this, super much easier. I didn't visit much of anything at all, right? I didn't fly all over the place like I did with the onto. On your homework, where you're going to be doing the bottom row, what's going to happen is the 1 to 1 is the one where you go all over creation, and the onto will be these, right? These kind of things roll reverse a little bit. Okay. Any questions so far? Okay, I think I can probably safely excise this one. Hold it here. And let's look at, I want to show that the image of F contains the kernel of G. So let A2 be in the image of F. So A1 goes to, let's say, A2, that would be 1. We want to show that this goes to 0 if you push it on this way, right? Well, the easiest thing perhaps to know is this goes to B1. And this goes to B2. Right? And so A2, whatever it is, has to go to B2, commutativity of the diagram. Let's push B2 further, and if I push it on this way, what do I have to get? 0. Good, because of the fact that middle row is exact. So when I push this over here to some A3 and down here, it must go to 0.
But that map is 1 to 1.
But this map is 1 to 1. Therefore, A3 is equal. And there you go. So the last bit, which is almost always kind of a tough one, is the kernel is contained in the image. Ran a white or something. So for this last bit, I want to show that the kernel G is contained in the image of that. So last trick. So let's let, say, A2. We'll have to do a little bit of chasing here. So we have an A2 here that goes to 0. I gotta find something over an A1 that goes to it. Well, okay, once again, I don't know this is exact yet, so there's no necessarily pullback. But I do know that that has to go to 0 like that. Everybody okay with that? A2 goes to 0, so going this way, I get 0. So going this way, I get 0, which whatever this B2 is down here, it goes 0, right? And the middle row is exact. So there is a B1 back here. It goes to B2. Right? Okay, so now what? Well, I need to work my way up to that top row. And I just, at this point, I don't have enough information. So I'm gonna go the only way I can go, which is down. Go down here. But this B2 must go to 0, right? Because again, the image of this is contained in the kernel of this. And by commutativity of the diagram, whatever this B one here goes to B two, goes to zero, that means C one goes to zero. This map is 1-to-1, so C one is zero. This vertical bit is exact. And B one goes to zero. This is in the kernel. Kernel, Actually goes from B one to C one. That means that there must be some A one that goes here. Now, I'm really kind of hoping that A one goes to A two. But I don't have any compelling evidence of that yet, so I'm gonna do this. A one goes to A two prime. But again, with the same trick that we've done before. A one goes this way to B two, so A two prime also goes to B two, right?
One. Yeah.
Right. And good, this function is 1-to-1, so what do we have? We have A two goes to B two. And A two prime goes to B two. Therefore, A two equals A two prime. And there we have it. In fact, I think that was even perhaps a little bit easier. Well, I know I did visit everything except the bottom right corner, but I think that was even easier to get onto. Any questions on that? All right, well, diagram chases, they're a lot of fun. I'm gonna give you one more theorem for your notes, and let me discuss it. This one's actually on your homework. This one is often referred to as the snake lemma, because it does a little snaking, and I'll show you what I mean by that. Theorem. Consider the following commutative diagram with exact rows. Diagram. Of our model homogeneous system. With exact rows. Right here. This is one, two, three. So in particular, let me just make sure that I'm reasonably clear on this. The image of F1 is equal to the kernel of F2. F2 is onto, but F1 is not necessarily 1-to-1. Maybe, maybe not. H1 is 1-to-1, and the image of H1 is equal to the kernel of H2, but H2 is not necessarily on.
The last one should be B3, right?
Yes. 1, 2, 5. Yes, it should be Then there is an exact sequence. From the kernel of G1, kernel of G2, kernel G3, co-kernel G1, co-kernel G2, co-kernel G3. And so, and let me actually, before I finish the statement, I'm gonna put that statement here. Well, let me remind you. If you have some homomorphism from A to B, then the kernel G, or I'm sorry, the kernel of that is the stuff, A and A, such that F of A equals 0, and the co-kernel of A, or co-kernel of F, so of course, the image of F is a submodule of B, and when you take B and mod out by whatever that submodule is, this is the co-kernel. Additionally, oh, right. I guess I did tell these things something. Alpha 1, alpha 2, beta 1, beta 2. Additionally, if F1 is 1 to 1, yeah, F1 is 1 to 1, so is alpha 1, and if H2 is on 2, so it's beta 2. This is actually a very fundamental theorem, and a lot of the machinery that makes stuff in homological algebra work. And let me, this is a homework problem, I want you to work out some details. But these alpha 1, alpha 2, beta 1, beta 2, again, this is math, so it should be easy. These are induced by the F's, the alphas are induced by the F's, and the betas are induced by the H's, right? So for example, how do you get from the kernel G1 to the kernel G2? Well, the kernel G1 is a subset of this, and the kernel G2 is a subset of this. And so just use F1 on something in the kernel, and you have to make sure you get something in the kernel here, right? You gotta make sure it's well defined. But once you've got that, this is a restriction of A1, then it should be a homomorphism. And so you need to show that the image of alpha 1 is equal to the kernel of alpha 2, but of course the exactness up here is going to be a huge help, right? The same thing here, when you're going from, say, the co-kernel G1 to the co-kernel G2, you're really going B1 mod the image of G1 to B2 mod the image of G2, and use that H1 to take the coset representative here. You gotta make sure that that's well defined. It's a homomorphism and it does what you want, but it's not too bad. The interesting part about the snake lemma is the snaky part. That is to say, how do you get from here to here? The kernel of G3 is some subset of here, and then you get all the way over the co-kernel of this. So how do you get from something here, some A3 that goes to 0, to something of the form B1 mod the image of G1, right? That's what's kind of weird, right? And I'm gonna play this fast and loose because I want you to think about the details here, but let me ask you this, let's be totally naive. This is gonna have a bunch of holes in it, but that's what you guys are here to paste up. How do I get from A3 to something, B1 to a coset B1 plus image G1? What's that? Right, so I could go backwards here, right? Because there certainly is an A2 that goes here. Everybody agree with that?
Yeah.
Because it's onto, right? And then I could go down here to B2 here. But see, what must happen is B2 must go to zero, right? Just by its very nature. Any A2 I pick here goes to a B2 that goes to zero, right? Which means there's a B1 that goes here. So, B1 is equal to, oh, this is really sloppy, but take whatever your A3 is, take F2 inverse, and by F2 inverse, I mean a pre-image, right? Then apply G2 and get a pre-image. Now, tell me why looks like it could be a train wreck.
F2 is not 1-to-1.
There's all kinds of problems with this, right? First of all, my choice of A2 is probably not unique. There's probably infinitely many A2s that I could have chosen, right? Once I make that choice, the G2 is not a problem because that's a function, right? Then I've got to choose another pre-image, right?
Yeah,
Now,
that's-
if there is a pre-image, it should be unique because this is 1-to-1, right? But I've still got this well-defined image problem. Right? Is this well-defined? Is the pre-image well-defined? The answer is no. But it is unique up to something in the image of G1, right? That's what you will discover. The A2 that you pick in that first step, there might be many of them. But no matter, you pick one A2, you pick another A2, and you will find that what you have differs by an element of the image of G1. And so you're good to go. You're well defined if you're going to actually. Okay, any questions on that? So let's look at, next step here. So this is theorem 648. Let's let R be a ring. You can assume commutative identity. Zero. A, B, C, zero. Be a short exact sequence. The following conditions are equivalent. Number one, there exists an R module homomorphism let's call it K, it goes from B to A, such that when you do F and then you do K, you get the identity function on it. Number two, there exists an R module homomorphism H, let's say from C to B, such that when you do right, do H and then G, get the identity on C. And finally, three. Uh. Is isomorphic. And I'll clarify what I mean by this. This is isomorphic, to the sequence, zero, A direct sum C, from C. This particular short exact sequence, where out of A little a is A zero and high C of A comma C, C. In particular, B is isomorphic to A sub C. By the way, I don't think I'm gonna do this complete proof because part of this I think is gonna come up. I want you to do a little exploring the next homework set, but, here's parts. One, zero, A, B, C, zero. Is isomorphic to zero, A sum C, C, zero means there is a commutative diagram. Oh, so this is F and this is G. This is what I call out of A, and this is out C. So what I mean for the sequences to be, or for the short exact sequences to be isomorphic is, here's the one that I gave you, top row. Here's the specialized one, right here. You should be able to connect these with this homomorphism, actually isomorphism. The short exact, or the short file limit tells you that if you can make this a commutative diagram, and these are the identities here, then this must be an isomorphism. But you need to be able to make this, commutative diagram with the identity on A and the identity on C. All right, this is what it means. And my second remark is, and remark two is kind of a definition, two, definition. If and the C zero satisfies one, hence all of conditions in 648, then we say it is a split exact sequence. What it means to be a split exact sequence is, it means not just as the middle isomorphic to the end pieces, but it means essentially you can run the sequence in reverse, right? There's a K goes right here, and an H goes back here. Okay. Any questions on that so far?
Yeah.
Yes.
So I think last week we asked if this property characterizes the split exact sequences, and you said that this is only the case if B is finally generated or A, B, and C.
Well, you're only guaranteed, so for example, if you have an Ethereum ring and all the modules are finitely generated, then you can prove that if the middle is the direct sum of the two ends, then it is in fact split exact. So if you're going to go hunting for a counterexample, that is something where the middle is isomorphic to the bookends, but you don't have these two conditions here, you need a module that's not finitely generated. Yes.
The definition of two isomorphic sequence, it is necessary that the extremes are the same, or?
Well, you could generalize it to isomorphic, yeah, right, but here, so if it's isomorphic, if you had an isomorphism here, then you could take the inverse isomorphism and add it all together. You can do it a little bit more generally, you're right. Okay, so let's see. Right here. I think we can, let's go a little bit going on this. Actually, you know what? I'm going to give you all a definition. I'm gonna come back and prove this just because we're kind of low on time and I don't want to get all foaming at the mouth and excited about this and then keep you all over. So we'll prove this theorem, or at least most of it, next time. Let me give you a definition. This is probably the next section we're going to talk about. So here's my little preview in our last bit. One of my advertisements about modules early on, as I said, sort of an R module is sort of like a vector space over a more general ring, right? So you don't have something as nice as a field, you have a module over it, right? But we've seen modules, like for example, if your ring is a pretty nice ring, like the integers, then every abelian group is a pretty module, or is a module over it. And some of these, like for example, Z6 is a Z module. Every element of Z6 is torsion as a Z module, right? What is the big thing about vector spaces, right? What's the most important thing about vector spaces? Is vector spaces all have basics. They all have basics, right? That's a big thing about them. And actually, because of the fact that a vector space has basis, if you give me any vector space in the world over a field, then all you have to do is understand how big its basis is, and then you understand it up to vector space isomorphism, right? Because basically the vector space is just some number, it's a direct sum of some number of copies of the field, right? This sort of necessitates following definition, and you'll see the familiarity here. Let M be an R module and X in M a non-empty subset. We say that X is linearly independent if given any X in X and R1, R2, Rn, and R, the relation R1X1 plus Rnxn equals 0 implies Ri equals 0 for all I. So this should be very familiar, the definition of linear independence. It's exactly the same as it is when you're talking about vector spaces, and as you may suspect, three modules, when we get to them, are the analog of vector spaces for modules. That is, they have a basis, and any element in there is a unique linear combination of that. But we'll get to all that later. Any questions? Okay, well, we will see you folks by Wednesday.